Okay, so this is 1610 calculus, and we begin with graphs and models. So a lot of this, well, in this beginning chapter one is basically just um, review from your like college algebra. So hopefully this is not too remedial, okay? But I'm just teaching what I'm supposed to. All right, so graphs and models. Um, a tried and true method for graphing is point plotting. So um, maybe you missed how to graph a particular kind of function in your education. How the heck do I go about graphing it? Well, you just make a table of values. For example, number 10 here, we have absolute value equation. And maybe you've forgotten, this is basically, it looks like a formation of birds, right? This would be your parent graph, and then you could use translations to move this about in the plane. As hopefully you learned that in college algebra. But if not, you can go through the process just listing a bunch of points and then graphing the points, right? So we list a bunch of points. Hopefully we get it centered in a particularly important place. We'll talk more about important places throughout calculus. We put the numbers in here, so the absolute value of -2 is +2, 2 minus 1 is 1, and so on, right? So absolute value -1, 1, 0, and then -1, and then 1, whoops, is it 0 again? And then 1. Okay. And you go over the xy plane and plot those guys. So -2, 1, -1, 0, 0, -1, 1. Oh, yeah, so that's what it looks like. So even if you've forgotten, you can get kind of a nice little picture here. And then on top of that, you can kind of remind yourself, oh, all I have to do is take this graph and then shift it down by 1. Okay, so that was kind of our translations that we used. Okay, so when you're doing graphing problems, probably the most important thing, or one of the most important things to help you along your way are the x and y intercepts. So let's go x/y intercepts. And it's fairly easy. For the x-intercept, just let y be 0. For the y-intercept, let x be 0. So you're just sort of substituting in the opposite variable with 0. So now let's take a look at this guy. So we have a relation here. Not sure if it's probably not a function, right? So it'll probably fail that old vertical line test because of this y² thing over here. So anyways, it's a little bit different than just finding the x-intercepts of, I don't know, a parabola. So anyways, let's go at it. So the x-intercept, you let y equal 0. So have 0 is x³ minus 4x. And then I have this little polynomial equation to solve. So you use all your methodologies. Here we have x times x² minus 4. I could continue factoring the x² minus 4 if I wish. So I have x times x minus 2 times x plus 2. Okay. And then I'll have 3 x-intercepts. X is 0, x is 2, and then x is -2. Okay. So those will give you the ordered pair 0, 0, 2, 0, and then -2, 0. Okay, so there's 3 x-intercepts. What about y-intercepts? So for the y-intercepts, you let x equal 0. So I'll have y² equals 0. And then what squared equals 0? Well, the only answer there will be 0, of course. So our y-intercept is just 0, 0. Okay. Okay. So they get more and more complicated, which is not something you see polynomials, you see rationals, and you don't really see anything other than that in your college algebra classes. So we'll get a chance to explore some more complicated relations here. I guess this is a rational equation, maybe not as complicated as what you've seen before, or maybe it's more complicated rather. let's go ahead and get the x and y intercepts here. So for the x-intercept, again, you're letting y equal 0. Okay? And what you're ending up with is a rational equation. So you have to be considerate. You have to remind yourself, okay, when I'm solving a rational equation, I need to make sure that I don't accidentally get something that causes this to be 0 in the denominator. So you can't have like negative 1/3, obviously. Okay, so that being said, multiply both sides by the denominator, and you end up with just setting the numerator equal to 0, right? Just apply where you guys were kind of trained to do it in high school. You said just take the numerator and set it equal to 0, so long as the denominator is not 0. Okay, so anyway, 0 is x times x plus 3. And we get 2 intercepts, x is 0, or, x is negative 3. So 0, 0, which will also be a y-intercept then, and then negative 3, 0. Right. So for the y-intercept, you're letting x equal 0, so y will equal 0 squared plus 0 is 0, all over 3 times 0 plus 1 squared is 1 squared, that's just 1, so of course that equals 0, and our y-intercept then is, as stated, 0, 0. Okay, so if you remember back in college algebra, you went through the process of solving all these different kinds of equations. You know, why was I doing that? Well, sometimes if you're looking for graphing, which you'll spend a lot of time in calculus worrying about graphing these things, you need to apply those methods, otherwise you may screw it up. So another kind of equation we worked with was the radical equations. So for example, 26, y is 2x minus the square root of x squared plus 1. Okay. So here you see you're going to have some radical stuff to deal with. We find the x-intercept. Again, you're letting y equal 0. So I got 2x minus the square root of x squared plus 1. To solve this kind of equation, you want to isolate the radical expression. So I'll have 2x equals square root of x squared plus 1. Square both sides, you get 4x squared is x squared plus 1. Okay. Now we have a quadratic equation. One other thing is when we get our solution, because it began with a radical and we rose both sides to an even power, we would have to check this solution to make sure it even worked. Okay. Anyways, let's carry on. Move the x squared over, I get 3x squared is 1. Divide both sides by 3. X squared is 1/3. So apparently x is plus or minus root 1/3. Okay, so we get two solutions there. You technically have to go and check those. We can do that kind of, I guess, right now. So I got 2 times root 1/3 minus the square root of root 1/3 squared is just going to be 1/3 plus 1. And then you got 2 times the square root 1/3 minus, and this should be 0 at the end of the day when all is said and done. 3/3 plus 1/3 is 4/3. So a square root of 4/3 is 0. And then we get 2 over, because you know the square root of 1 is 1, so I got 2 over root 3 minus square root of 4 is 2 all over root 3 again, and of course that's equal to 0. Let's try the other one. That one ain't gonna work, right? Because the factor that's going to screw us up is when we put in a negative root 1/3, we'll end up with negative 2 over root 3 for our first term. The second term will be the same. When I square a negative, it will become positive 1/3. So I can write 2 over root 3, and you know, just testament to what I was talking about. You know, you have to check your solutions when you're dealing with radical equations. So the only solution here is actually the positive one. And so therefore we have x-intercept of root 1/3, comma 0. Right? Okay, let's get our y-intercept done. And I'm just going to move up here. Okay, so for this guy, for the y-intercept then, you're letting x equals 0. So y will equal 2 times 0 minus square root of 0 plus 1, which of course will just be 0 minus root 1, which is equal to 0, minus 1, which is minus 1. Okay, so our y-intercept then will be 0, negative 1. And then that's it. So we got the one x-intercept, the one y-intercept. Okay, so great, good stuff. Let's see what else we got. Symmetry. So in college algebra, you probably talked about odd and even symmetry, and you remember that well. On top of that, we need to worry about just general relations. So when you're talking about odd and even symmetry, there's kind of a tacit assumption that you're dealing with a function. But more and more, you're going to see, hey, functions aren't the end of the story. We have relations as well. So when we talk about symmetry for us now, we're going to think about the three version types. Okay? So the odd and even symmetry are still in these categories. It's just we don't call them that. We call it origin symmetry and y-axis symmetry. But because now it's not necessarily just functions, we're also going to include x-axis symmetry. So sort of a reminder of how this works. If you have sort of a parabola, we would say that would be our even symmetry, right? So in particular, if you take a value x comma y or a point on this graph x comma y, you'll also have the corresponding point negative x comma y. Okay. So this is called even symmetry. The book will call it the y-axis symmetry. The next kind of symmetry, then the x-axis symmetry. So if you have like a sideways facing parabola here, and you have the point x comma y on the graph, you will also have the corresponding point x comma negative y. And that's called x-axis symmetry, excuse me. Finally then, if you have sort of the cubic function is always the one they give you, and you have point x comma y on the graph, you'll also have the corresponding point negative x comma negative y on the graph. Okay? And in that case, that's the odd symmetry that we're familiar with, but it's also then the origin, they'll call it the origin symmetry for now. Okay, so to see whether or not a particular function has a particular type of symmetry, what you're going to do is kind of a replacement of variables, and the replacement will go along the lines of these replacements. Okay, so if you want to see if something has odd symmetry, you're going to replace the x and the y variables with negative x and negative y, and then if the thing is unchanged, if the resulting equation is the same, then it has that particular type of symmetry. So let's look at number 30. And here we have some sort of kind of cubic, maybe some sort of depressed cubic, I don't know. So anyways, we have y-axis symmetry to start out with. So for the y-axis, we're going to replace x with negative x. Okay, so I'll have y is negative x cubed plus negative x. And simplify it, and we get negative x cubed minus x. And then you ask yourself, is that the same thing as the original equation? And of course it's not. It has opposite signs, so there's no way this is y-axis symmetric. So new. Then you go to x-axis symmetry. I would say no as well. A good indicator for x-axis symmetry is if you end up, if you have, well, let's just go at it. So for x-axis symmetry, you have x comma y, and you're going to replace the y with negative y, right? So I'll have negative y equals x cubed plus x, And then we take a look at this and this. Are they the same? And no. I mean, they're the same at certain points, certainly. 0, 0 would be a point where they're equal, but it needs to be the same for every point considered. And that's not going to be the case here. Obviously, if you multiply both sides by -1, you're going to get this equation here, and we already said this is not the same as this, so therefore this won't be the same as that. Finally, let's do the origin symmetry. So for the origin symmetry, we're replacing both x and y with -x and -y. So let's go with that. We got negative at y is -x cubed plus -x. And then we're going to go ahead and simplify a bit. Negative y is -x cubed minus x. And if you multiply both sides by -1, you get the original equation, which tells us this has origin symmetry. So yes. Okay, so that's how you go about that. Let's look at using symmetry and then intercepts to graph functions. Right, so we will be spending a bit of time just graphing functions and looking for their particular important points, their maxes, their mins, and that sort of stuff. So usually one step we'll want is using symmetry and your intercepts to make graphs. So using symmetry / intercepts. Okay, so look at 44 this time. Y, it's almost the same exact guy. It's another one of these cubic things. X cubed minus 4x. Okay, so I'm thinking it probably has the origin symmetry. Very quickly, let's get the symmetry out of the way. It's kind of time consuming. So for x-axis, or we do y-axis first, right? So that would be the even symmetry idea. We're replacing x with -x, so we'll have y equals -x cubed minus 4 times -x. So that would be -x cubed plus 4x. And clearly that's not going to be the same thing as this, right? You put in points, you'll get out other points for your y value. So if you put in 1 for x, you get -1 plus 4 is 3. So at 1, you'd get 3. Over here, if you put in 1, you'd get -3 as your corresponding y. So these aren't the same pictures, basically. So no, it's not y-axis symmetric. How about x-axis? And now we're replacing y with -y, and it'll be the same kind of dealio. Here, if you put 1 in for x, you'll get 1 minus 4, which would be -3, and then y would equal 3. Up here, if you put 1 in for x, you get 1 minus 4, you get -3. Okay, so on this graph, you'll have the point 1 comma -3. On this graph, you'll have the point 1 comma +3. So they can't be the same thing. Okay. All right. And then finally, origin symmetry, which we suspect is going to work. We'll have -y is -x cubed minus 4 times -x. So -y is -x cubed plus 4x. Multiply both sides by -1. Y is x cubed minus 4x. And that's it. It is origin symmetric. So we can sort of circle that or something, remind us later that we have that kind of symmetry. Okay, so now I'm going to get my x and y intercepts to kind of tack that down. So the x-intercept, you let y equal 0, so I have 0 equals x cubed minus 4x. Factor out the x, so get x times x squared minus 4, and then of course it'll be x times x minus 2 times x plus 2, and I have 3 x-intercepts, 0, 2, and negative 2. Finally, for my y-intercept, you're letting x equal 0, so that'll just be 0, and I get 0, 0 there. Okay, so finally then I can sort of come over and do a graph, a sketch of what the picture should be. You may or may not remember from your college algebra days that if you have this kind of polynomial, it'll have this kind of behavior where if it's a positive leading coefficient, it'll go towards negative infinity in the negative direction and positive infinity in the positive direction. So our end picture should look something like this. And it has this origin symmetry, so if you have this point here, you expect this point down here. If you have this point here, you expect this point right here. And yeah, that's pretty much it. Okay, let's now carry on to finding intersection points. So another important tool for our work when we get to finding area underneath curves, which is a big part of calculus. You know, what is calculus? So it's 50% in finding the slope for general curves, and then 50% finding the area underneath those curves. And they're both related to each other in a kind of clever way. Anyways, we'll need to be able to find intersections of curves. And you can set equations equal to each other, or you can do addition method, that sort of stuff. Let's just take a look at two of them, I guess. So 58, I have the system 3x minus 2y is negative 4, and then 4x plus 2y is negative 10. Right? So here you can do the addition method, and of course these variables just cancel right out, and you get 7x is negative 14, and so x is negative 2. And then you take that guy and you plop him back into any equation that has both unknowns. So you go 3 times negative 2 minus 2y is negative 4. So negative 6 minus 2y is negative 4. So negative 2y is positive 2. So y is negative 1. And the solution to that system then, negative 2, negative 1. Okay. Let's look at 62 then. We have x squared plus y squared is 25, and then our other guy is negative 3x plus y is 15. Okay, so what are these things that we're dealing with? The first guy is a circle with radius 5, and then the second guy is an equation of a line. Let's rewrite it so it's more familiar, right? So y is 3x plus 15. So if this has radius 5, 15 is way out there. At 0, it's at, all right, so let's get some points for this. So when y is 0, x is negative 5. Okay, so we got a point right there on the circle. And then when x is 0, y is 15. Okay, so negative 5, 0, and then 0, 15. So I'm thinking maybe something like this. Okay. How do we figure out those points of intersection then? Well, obviously one of them we have already. It's just 0, 15, sorry, negative 5, 0. Let's get the other one. So I'm going to do the substitution method this time. I'm going to plug this guy into here. So I have x squared plus y squared. Y squared is the same as 3x plus 15 squared equals 25. Just to make the math a little easier on my brain, I'm going to factor a 3 out of this. So it'd be plus 3 squared is 9, and then times x plus 5 squared is 25. Believe it or not, you can do that. And then x squared plus 9 times x squared plus 10x plus 25 is 25. And then distribute the 9. So x squared plus 9x squared plus 90x plus 225 is 25. Okay, it's quadratic, so I want to combine like terms. I got 10x squared plus 90x, bring the 25 over, plus 200. Then I can factor out the 10, so I get x squared plus 9x plus 20. And then I can factor that guy, so I get x plus 5, x plus 4 is 0, so x is -5, x is -4. And then back substitute to get your corresponding y values. So when x is -5, y obviously is 0. And that gives us this first point of intersection. And then when x is -4, y is apparently 3. So that gives us this other point here. Okay. So there's a bit of a review. Next time we'll look at linear models and rates of change, and then functions and graphs. Okay, thanks.